hair, long beautiful hair. Okay, so what we're looking at here is another problem from Unit 6 with forces, but this time we're going to look at connected objects that are not only moving horizontal, but also vertical over something known as a pulley. So in question 9.1 here, what we have is a 10.4 kilogram block sitting on a frictionless horizontal table. So here's the table up here. Whoops, let's draw that better. Here's a table. And our block is sitting up on the table. So here's our block. And it's got a mass of 10.4 kilograms. Okay. The block is attached to a horizontal ideal string, so it doesn't slip, doesn't have any mass. And it goes over an ideal pulley, so it's just changing the direction of the string. Okay, we don't have to worry about it. If you're doing more advanced stuff, that'll have a moment of inertia, but we're not, so who cares? So here's an ideal pulley. So bloop, little circle. Here's the string. It goes over the pulley and down. And down here, there is another block that it's hung to. And this is also 10.4 kilograms, and it's just hanging there. Okay. What we're looking for is what is the acceleration of the block on the table. Now, kind of neat point about this is the acceleration of the block on the table is also going to be the acceleration of the block out here, which is falling down because they're connected rigidly. And we're also looking for this tension in the string. So let's just think about this for a second. Before we start getting into math and whatnot, let's just think about how are these objects moving? Well, there's no friction here to hold the block on the table. So any amount of force acting on it from the string, any amount of tension will cause it to move. Okay? Any amount, even the slightest bit. And we know that this tension is an action-reaction force. It's acting equal and opposite directions. So even though it's acting to this right here, it's also acting up, because up is the same as left. Okay? Now what we're actually doing looking at this is we are going to take this horizontal and vertical system, and if we think about what's causing them to move, well, there is a weight acting on this hanging block here, right? Weight equals a mass times a gravity. And if we wanted to, there's two ways to think about this. The way I like to think about it is, what direction are these objects moving? Now, the block over here is sliding across, and then it's going down. So I like to think that the direction they're moving is the positive direction, and the opposite of that is negative. What that means is that up top on the table, the right is positive and the left is negative. For the vertical block, down is positive and up is negative. Okay? If you want to think about it like that. Now some people, this is kind of a sidebar, some people like to do this. Some people like to redraw their blocks side by side. And then this is actually the weight equals mg here. All we did is we took a curved system and we just kind of bent one of the edges up. So I took this bent edge and I lifted it up so that now I can just say this is the direction. Okay, I'm just saying this going to the right is positive. And that's what this picture is up here. We're just saying now that, hey, look, the right is positive, the direction of motion, the left is the negative direction. You could do that if you wanted to. I like personally keeping my picture as it is and just thinking about directions of motion and including, for vertical, positive and negatives, and for horizontal, positive and negatives. But it's really up to you. Okay? From this point, though, now we actually have to start figuring out how to solve this problem. What can we do here? Now, there's two ways we can go about this. We've got two objects here. So if we drew a free body diagram, for our top object, it would have a tension acting like this. For our second object, the one hanging, it would have a weight equals mg and a tension acting back on it like that. So if we wanted to, with these two free body diagrams, we could write two F equals ma equations regarding that, and then see where that would take us. But what we're looking for initially is just the acceleration of the block on the table, which is the block down here. The accelerations have to be the same. And what we could do then is we could take a system, the entire scenario, and we can say the sum of the forces will equal ma for that. In doing this, remember, down is positive, up is negative, right is positive, left is negative. And if we sum all of our forces here, we're going to have a weight minus a tension, positive weight minus the tension, plus another tension, and this will equal the mass of everything we include inside of our system. So that's the 10.4 kilogram block and another 10.4 kilogram block. So we're going to have, what is that? 10.4 times plus 10.4 is 20.8 kilograms multiplied by the acceleration of the system, or both the objects. We quickly see that these tensions force each other away, and we can replace the weight here of just the weight of the block that is falling. So we know that this weight here is the 10.4 kilogram block, the mass, times the gravity, 9.8. And this will equal 20.8 times the acceleration. If we go ahead and just divide by that 20.8 then, on each side, we'll see quickly that 10.4 over 20.8, we could reduce that to just 1/2. So this is going to be like 9.8 divided by 2, because these have reduced down to be 1/2. And that's going to equal the acceleration. So our acceleration then simply becomes 4.9 meters per second squared. So that's part A. For part B, when we need to find that tension, well, we have a great equation for this. We can use just this F equals ma equation in order to solve that. We can say that, hey, look, a tension equals the mass of this object here, which is only 10.4 kilograms, times the acceleration of that object, which we just found to be 4.9. And when we solve that, we get something approximately 51 newtons for the tension in the rope. If you wanted to, you could have used the equation weight minus tension equals 10.4 times 4.9, and then put in the value of weight here being 10.4 times 9.8. But that's just a little bit extra work that I don't want to do, so we used the upper equation here to solve that instead. Okay, so very similar problem to the connected objects we did in the past with the boxes, or with the either boxes pushing on each other or the boxes pulling a string, or the example problem we did with the truck and the camper. But this is very similar to the block of cheese and the mouse problem that we did as an example. And we just got to recognize that we've got two objects here. We can either write out two F equals ma equations or use the system to find the acceleration here. And then once we have that acceleration, we can go back and find tension by looking at our free body diagram again. Okay? Note that the big thing here was just recognizing what directions were positive and what directions were negative. A lot of people mess that up. A lot of people, even whenever they're drawing their second free body diagrams and they're breaking it up like this, they forget the positive and negatives. And if you forget that, that problem is going to go sideways on you real quick. You're going to get a lot of weird, wonky answers, and you don't want that. Okay? So we'll do some more examples of this. We'll see some more. But for right now, this is finished. Adios. And y'all take it easy, everybody.